38, 39. Let's consider we go to the page number 38. You can see this all regulators power good, HWPG, you can see this HWPG, all the regulators are generating this HWPG, and it is going to the IO controller, right? It is going to the IO controller. After the IO controller receives the hardware power good from all the regulator, it will generate EC power OK, right? It will generate EC power OK, EC PWR OK signal, and this is an input to the IO controller, because the IO controller is at the center of power management signal. We have already seen when EC receive SLP underscore S5, when EC receives sus B, when EC receives sus C, then it generate main on, sus on, and VR main on, sus on, and VR on. This sus on, main on, and VR on open up all the voltage on the regulator, all the voltage on the main board. So all the voltage regulator will give a hardware power good signal to the IO controller. After IO controller receive the hardware power good, it will generate EC power OK signal, and this EC power OK signal is being fed to the ME power OK, that is management engine power OK. So this is the relationship of how IO controller works in connection with the PCH, right? Okay, so we have seen signal up to ME power OK. Now let's check the next signal, which is LAN underscore RST. So what we'll do is we'll just copy this and we'll just put it over here, LAN reset, LAN reset, and you can see this LAN reset, you can see it is getting connected over here. I think the LAN value is not used in this schematic, and that's why it is going to be grounded. You see this LAN reset, this is the LAN reset pin inside the PCH, and here this signal is RSV underscore ICH underscore LAN underscore RST, and you can see this is getting connected because the Intel LAN is not used over here. Why this is grounded is because we are not using the Intel PHY devices. This is called PHY devices. The Intel internal LAN is not used, and so you can see this is grounded. Now we go in the data sheet and check the next signal. This is DRAM power good. Sometime in a schematic diagram you will find this as DRAM power OK, because this is a signal which is coming out from the PCH and going to the processor to indicate to processor that yes, that DRAM power is OK, because in PCH kind of board the memory controller is inside the processor, right? The memory controller is inside the processor, so there must be some kind of indication to processor that the RAM power supply is not okay, right? That the RAM power supply is not okay because the memory controller is inside the processor. Otherwise, in a board which is having north bridge and south bridge, this indication would be sent to north bridge because the memory controller is inside the north bridge. But here the memory controller is inside the processor, so a signal must be given from the PCH to the memory controller inside the processor to indicate that RAM power supply is not okay. So we'll see in the schematic diagram. This is DRAM power OK. As I told you, in the data sheet it is written DRAM power good, but this is same as DRAM power OK. This is output from the PCH and it is going to the processor. We can search over here. DRAM power OK is connected to PM underscore DRAM underscore PWRGD. So what we'll do is PM DRAM and PWRGD power good, and this is going to the page number 3. As you can see, this signal is going to SM underscore DRAM power OK. This signal indicates to the memory controller inside the processor that the RAM power supply is okay, right? That the RAM power supply is okay. And what is the next signal? After PCH indicates to processor that the RAM power supply is okay, and already all other voltages power okay indication has been done, that is power okay, ME power okay, LAN reset, these all power okay has been indicated to the PCH. So the PCH will indicate to the processor that now the RAM power supply is okay, and now what it will do, PCH will output stop underscore PCI to clock chip to enable the clock chip to generate the clock frequency. So what we'll do is we'll go to the page number 2, which is the clock controller. This is 9LRS3197. this is the clock chip, and as you can see this clock chip, what is the enable is CK underscore PWR GD underscore R, which is connected to the VR power good underscore clock enable. This signal is coming out from the VRM chip, the CPU core voltage regulator. In some kind of clock generator you will find CPU underscore stop is basically connected with the stop PCI, but here this is connected to the plus 3V volt. So this stage is not required here because the clock generator is getting turned on in this schematic diagram after the core voltage regulator provides the enable signal, right? In some kind of schematic diagram you will find it CPU underscore stop, this pin to be connected with the stop PCI, and from where this stop PCI is coming, it is coming from the PCH. Alright, now what will happen, the clock chip will provide all kind of clock chip output to the PCH, and you can see this schematic diagram, all kind of clock is provided. So now you can see the PCH has received all power supply, reset, and now clock. And now what will happen, the clock chip has provided the clock to all the entire motherboard, and now it will turn on. After this step, the PCH will provide to the processor power good signal, proc power good, and we can see over here proc power good, PROC PWRGD, proc power good, I think proc power good, and you can see this proc power good signal is generated by the PCH, and this is H power good, and this H power good would be going to the CPU. H power good would be going to the CPU, and you can see this H power good is going to the VCC power good 0, VCC power good 1, and this is the final step. This is the final indication to the processor, a final indication to the processor of power good. This is the last power good which is generated by the PCH. Always what we have to keep in mind is the correct power sequence that we have to trace, and what you have to do is you have to just look at which kind of chipset you are having in your board. If it is Intel Series 5 chipset, you just go into the electrical characteristic, power sequencing and reset signal timing, and you will find this chart, and you have to just follow the entire tracing by following these signals, right? By following this signal. And what is the next step? After the PCH provide power good to the processor, the PCH will generate sus underscore stat. And what do you mean by sus underscore stat? Sus underscore stat means suspend status. Now the board is entering from a low power state to fully turn on. So sus underscore stat will be given high value. Sus underscore stat will have high value during turning on, but not this signal is not used in all kind of board, and we can see over here in this board only whether it is used or not. Suspend status is sus underscore stat, and you can see this sus underscore stat is not used. The cross is missing, but this is not used. There is some mistake in this schematic diagram. You see the cross is not used, but this sus underscore stat is not used over here. Now we find the next signal, and the final signal is PCH generates PLT reset. This PLT reset means platform reset, that is all the other IC including processor will get a reset signal to start, right? Reset, what do you mean by reset? Reset is a knob, you know, reset, we press, we reset button, then everything turns on. Similarly, PLT reset is the final reset, platform reset. So PCH will generate PLT reset, and we can see over here PLT reset, and you can see this PLT reset, and this PLT reset is fed to an AND IC. You can see everywhere this PLT reset is fed to the Realtek IC. Everywhere you will find this PLT reset. PLT reset is fed to again another IC. This PLT reset will also be fed to the IO controller. Yes, this is also fed to the IO controller. So this is platform reset. And after this, the CPU will read at the BIOS chip, the first address at the BIOS chip, and this is how we trace a motherboard. So what we have to do, the first step is to identify the kind of Intel chipset is present. If it is a dual, if it is a north bridge south bridge type board, identify which south bridge is present. If it is a PCH kind of board, identify which kind of PCH is connected. If Intel series 5 chipset, then look for the data sheet of Intel series 5 chipset. If it is a HM67, look for the Intel series 6 chipset. In the next class, I will trace similarly an Intel series 6 chipset, and after that I will trace an Intel series 7 chipset, and after finishing this tracing in a theoretical manner, I will now again trace all of them practically using a CRO. That is, you can trace each of this signal on a CRO. To finish the class, I would just do another one good thing is that many of my students used to ask me how to edit AMI region. In many kind of boards, you will find that some kind of board restart often after 30 minutes, and that is the problem of a AMI BIOS. And we'll discuss a little about what is AMI BIOS and how to edit the AMI region, how to combine the AMI BIOS file. So I will just start with an AMI region, right? Okay, so let's discuss about the management engine platform, right? Management engine. This is very important. What is management engine? And I have a PowerPoint presentation from a very reputed company in Inventec, and this I found out in Google. So I'm using this document. And as you can see in the earlier platform, we have a processor, we have a MCH, we have a ICH. But in a newer kind of boards, this is an IBEX PIC based platform. IBEX PIC means Intel Series 5 chipset, and you can see the memory controller has moved into the processor, whereas the management engine has moved into the PCH, right? We go to the next slide, and you can see this is a next in the next slide. You can see in earlier kind of board you have a 3-chip solution where you have a processor chip, you have a Intel Series 4 chipset, and Intel Series 4 chipset means the North Breeze, and the North Breeze example of North Breeze are like AC82 GM45, AC82 GL40. So these are all Intel Series 4 chipset, that means North Breeze. So up to Intel Series 1, 2, 3 and 4 it was called North Breeze, whereas after 4 it is called PCH. So earlier it was a 3-chip solution. We have a processor, we have a Intel Series North Breeze, we have ICH, and now we have a 2-chip solution. So what happened in 3-chip and 2-chip, you can see the GFX has moved to the processor, the graphics have moved to the processor, whereas here you can see the graphic, the integrated graphic is in the North Breeze only. You can see the AMI is inside the North Breeze, whereas you can see the AMI is inside the PCH, right? AMI is inside the PCH, and you can see RAM is connected with the North Breeze because the integrated memory controller, the IMC is inside the north bridge, whereas the IMC has moved to the processor, so the RAM is connected to the processor. And we go into the next slide. Now what is management engine? The management engine is an independent processor core embedded inside PCH. So AMI is like a processor core which is embedded inside the PCH. And what are the important points? It operates independently from the main processor. It executes from ROM or RAM in the PCH. That is, this management engine can execute from RAM or ROM, that is internal RAM or ROM present in the PCH, or from main memory, or from AMI region of SPI flash. So it can execute from three places. It can execute from the RAM or ROM present inside the PCH, or from the main memory. Main memory means RAM, the external RAM, and from the AMI region. We'll go and find what is AMI region. Third is, it reads from the AMI region but never writes to it. That is, this management engine is a kind of processor core present inside the chipset. This will read from the AMI region. AMI region is present inside the BIOS chip. We'll find where AMI region is, and it operates independently from BIOS and OS but can interact from the BIOS. So this is a very important thing. The very important thing is AMI management engine is a kind of processor core embedded inside the chipset. It can read from three regions. What are the regions? It can read from RAM or ROM present inside the chipset, or it can read from the external RAM, or it can read from the AMI region present in the BIOS chip. And we go to the next slide. Now this is BIOS chip. This is an SPI BIOS chip. So nowadays the SPI BIOS chip, which is connected to the PCH, inside the SPI BIOS chip you will find the flash is divided into many kind of regions. And what are those regions? The first region is the first 4 KB. You can see the first 4 KB is designated as flash descriptor. This region will basically contains the layout of the BIOS chip, and it will have pointer to the other BIOS region. And what are the region? It is having AMI region, it is having GBE region, it is having BIOS region. AMI region, management engine region. GBE region means Intel internal LAN region, right? Intel internal LAN region, and here it's a BIOS region. So the SPI chip, that is 4 MB, 8 MB BIOS chip that is connected to the PCH, is divided into 4 parts. The first is flash descriptor, second is AMI region, third is GB region, fourth is the BIOS region. As you can see, inside the SPI BIOS chip there are many regions. So the flash descriptor have basically the rules for accessing this region, right? The access rules for accessing this region. So in the flash descriptor there are some rules, that is the host, if suppose we need the host BIOS should not access the AMI region, then here it would be written in the flash descriptor, it would be written that this region should not get access by the host, whereas this region should get only access by the management engine. So this all flash master access details are there in the flash descriptor. We go to the next slide, and this is a very good example of how a flash architecture is there in your notebook motherboard. We have a PCH. PCH is connected to the embedded controller, that is your IO controller, because EC is inside your IO controller, is connected via LPC bus. What is LPC? LPC is low pin count, and the PCH, as you see in the notebook motherboard, one BIOS chip need to be present, which should have BIOS, which should have the BIOS region, GB region, and AMI region, and that is contained inside this SPI flash. So this SPI flash should be mandatorily connected to the PCH. That is, in a newer kind of board architecture, this SPI flash needs to be mandatorily connected with the PCH. And your EC also requires BIOS, so a SPI flash would be connected to the EC, and the EC BIOS will be present in that BIOS chip. So if any BIOS chip is connected with the IO controller in a newer kind of board, then that means it will contain EC BIOS. It doesn't contain AMI BIOS. AMI BIOS is 100% in the SPI flash which is connected to the PCH. But another very important thing is that system BIOS. Where can be system BIOS? System BIOS can be in this chip also, system BIOS can be in this chip also, and it totally depends how the company, how the R&D has been done, and which company is placing the system BIOS into this and to this. But normally the system BIOS is put inside the SPI flash which is connected with the PCH. Now, since we had studied about these things, we'd go and look a very important use of AMI region. And what is the important use? The use is integrated clock control. How the board gets clocked and how does the AMI play a crucial role in providing the different clock configurations to the board, right? Different clock configuration to the clock. Let's see what is integrated clock control. Integrated clock control, that is ICC, allows board clock design parameters to be set using the firmware. That is, with settings in BIOS, we can have several kind of clock profiles. We can have several kind of clock profiles, and you can see the AMI region holds clock profiles for up to 7 different regions. And in the next slide you can very well understood, because this is an integrated clock control, and this is a very good crux of how AMI region is so crucial, and why when AMI region gets corrupted, why does your board gets restarted after every 30 minutes or after every 15 minutes. Why does it happen? And this you can understood from this diagram. So what is the first step? As we have seen in our data sheet, you can see after the PCH provides the DRAM power good to the processor, the PCH provides a stop PCI to the clock chip, and the clock chip will output the clock, right? The clock chip will output clock. So what happened here, you can see first the CK, the clock chip, CK505 is a clock chip. What is the first step? CK505 provides base clock to the PCH, right? It provides the base clock to the PCH. The clock hardware present inside the PCH will load defaults for the load silicon hardware defaults for clock. You can see what is the second step. The PCH loads silicon hardware defaults for the clocks. What is the first step? As you can see in our data sheet, the clock chip provides clock chip output to the PCH, and in this diagram you can see the CK505 provide base clock to the PCH. What is the second step? PCH loads silicon hardware for the clocks. What is the third step? Since AMI is an independent processor core present inside the PCH, it can execute from 3 locations. As I have told you, it can execute from 3 locations. One from inside AMI ROM, or from the AMI firmware, or from the RAM. Right now at this point of time, if AMI firmware is present inside the SPI flash, then this AMI boot ROM execute hands off to the AMI firmware. This is the third step. What happens? The data present inside the AMI firmware goes to the ICC register. ICC means integrated clock control registers, and the hardware circuitry then tunes itself with the data which is present in the AMI firmware. So if this AMI firmware gets corrupted, then your clock hardware will be configured badly, and if it gets configured badly, then this clock hardware which is present inside the PCH will generate wrong clock output, and when platform gets wrong clock output, then it won't work properly, right? So what is the fourth step? Fourth step is data which is present inside the MV firmware goes to the ICC register. ICC register loads this into the clock hardware. It generates clock output. And what is the seventh? BIOS now manages CK505 through SM bus, and the BIOS will BIOS will configure and manages clock through management engine interface. But if a AMI firmware is getting corrupted, then this data, corrupt data, will go to the ICC register. Corrupt data will configure the hardware clock, and a wrong clock will go to the platform, and that means the board will restart after some time. Usually it will restart after 30 minutes. So if you find any kind of i3 i5 boards getting restarted after every 30 minutes, the first thing that you have to keep in mind is your if AMI firmware is present, that means you have to edit the AMI region of BIOS chip, right? You have to edit the AMI region of BIOS chip. This one I am following it for the Intel Series 5 chipset. While I discuss for the Intel Series 6 chipset, I will again discuss about the integrated clock control. Now what I am going to discuss is how to edit the AMI region. How to edit the AMI region. Now to edit AMI region, you will require some certain kind of software, and you will require a WinHex, and you can get this copy from me WinHex. You can get this copy. I have downloaded it from the internet, having keygen also. So you can get this copy from me. WinHex. You will require the first software is WinHex. What is this? This is an hex editor. This is basically an hex editor. You can see over here. This is a kind of hex editor. I have also followed another hex editor, that is Ultra Edit, but I find WinHex to be much better than Ultra Edit. And the next software that you would require for editing the AMI region is UEFI tool. This UEFI tool is very important, and why it is important is that suppose you have a BIOS chip. Suppose you have a backup of a BIOS chip. I have a backup of Toshiba C850 BIOS chip. Now this is a complete backup of BIOS chip, but with UEFI tool, you open this UEFI tool, you load this BIOS region, you load this, and you can see you open this. Now you can see the AMI region. What is the version of AMI region? You can just locate the version of AMI region present inside the complete BIOS chip. So how it is important? Suppose your BIOS has got corrupted, right? And I have taken the backup of BIOS. Let's see Toshiba C850. This BIOS has got corrupted. We have to edit the Intel AMI region inside this BIOS, right? So first, what is the first thing? We have to open this BIOS using UEFI tool. We have to locate the version, and the version is 8.0.3. Always note, if your version is starting from 8, that means the chip that is present in the board would be Intel Series 7 chipset. If Intel Series 8 chipset is present, then version would start from 9. If Intel Series 5 chipset is there, version would start from 6. If Intel Series 6 chipset is there, version would start from 7. That is version start one after, right? Version start one after. So by UEFI tool, you can see the version. So what software you require? You require an UEFI tool. You require a WinHex. Now what we will do is that with WinHex you can open the BIOS file, and we have a Toshiba file over here. We'll just open it. Now this BIOS, we have deassembled the BIOS with the WinHex, but where to locate it? which at what address is the AMI region, at what address is the AMI region. A very simple formula is that you can just search, find hex value. Always note, in any kind of BIOS, your AMI region would start from 244650. This is the crux, 244650, and you can see at from this point your AMI region data is there. So what we have to do, we have to find a good AMI region, we have to copy that AMI region, and we have to paste there. We have to just paste here, and we have to just say, after pasting we have to save, and we can create a working BIOS file. So what you have to do, I have many backups of working AMI region, and you can see here again, we open the UEFI tool, we open the file Toshiba C850, right? We find the AMI region version 8, right? Version 8.0.3. I have OK version 8.0.3 also. You see V8 series, I have OK V8 series. You can get these backups from me, definitely. You can get these backups from me, no problem. The version 8.0, right now I don't have version 8.0 and 8.1 is same, but you should always look for the exact version. But here right now I have version 8.1. So what I will do is, I will open this version 8.1. I will open this version 8.1, right? What I will do, I will control A, control C, I will just control C, and here I will do right click, beginning of block, and I will do control B, right? Control B, so the click, and now I will save. Now my BIOS file is completely saved. So what I have done, I have opened the corrupt BIOS file, corrupt BIOS chip using WinHex. I have located the AMI region, and how located? 244650. This you have to remember. You go to the BIOS AMI region. What I will do, I will open a right AMI region which I have made backups. You will control C, control A, and just right click beginning of block, and just control B, and the clipboard data would be written, and just you can save it, and this will create the working BIOS file. That will create a working BIOS file. This is one way of doing this. And I find this to be much easier than any other way. But I will also tell you about the next way, how to create an working BIOS file, how to edit the AMI region. So I will again repeat what I have done. We have to keep two softwares. What are those two software? One is UEFI tool, another is WinHex tool. What we will do, we'll open the UEFI tool, we'll open the BIOS file, and we can check the AMI region version. What is the AMI region version? It is version 8, and I have already backups of version 8. So now what I will do is, I will use WinHex to open the corrupt BIOS file. So I open it, Toshiba C850. Now I will locate the AMI region, and how to locate? Locate is very easy. Just go into search, find hex values. Always remember, in any BIOS file, your AMI region would start from 244650. Just put it over here. Open the correct AMI region again with the WinHex. Control A, Control C, and just right click beginning of block, and just Control B, and you can just save. You can just save where you have to put it, and your BIOS file would become okay. So this is This is one way of doing this. I will describe the another way, that is using Intel FITC tool. Using Intel FITC tool, right? Intel FITC tool. So I have told you one way of the editing the IME region. I will tell you the another way of doing editing the Intel IME region. And what is the other way? Other way is using the flash image tool, and we call it FITC tool. And you will find FITC tool. I have FITC tool for all kind of version. So if your chipset is Intel Series 7, then you have to use the flash image tool version 8. And if your chipset is version is 6, Intel Series 6, then you have to use flash image tool 7 series. If your chipset is 8, then you have to use flash image tool 9 series. Right now I have an example is Toshiba C850, which is having Intel Series 7 chipset. So we are going to use the flash image tool. We open it, we'll FITC, we open the FITC tool, and you can see here you can just put, like, if it is HM77 chip is there, then you open the faulty BIOS chip, right? Faulty BIOS chip, and we open the faulty BIOS chip. You can all files, click all files, and here you can open the Toshiba C850. Yes, you just open Toshiba C850. Now this Toshiba C850 has been deassembled, and you can see Toshiba C850 folder has been created, and inside the folder you will find, inside this folder you will find all the region to be extracted, right? All the region to be extracted. Now what we have to do is we have to just use the correct IME, which we have a backup, right? So yes, and we will just select the correct, IME region, right? Correct IME region. So we have a copy of correct IME region from version 8. We'll use the version 8, we'll OK, and we'll just build. We'll click build image, right? Now we have build image, and you just go over here, and you can see this output image has been created, and this is your corrected file. This is very easy, right? This is very easy. What we have done, we have opened the FITC tools, right? We have opened the faulty BIOS. We have opened the faulty BIOS, right? We have opened the faulty BIOS. Here all files, use all files, open the Toshiba C850, right? Now we have just opened it, and your all file would be deassembled, right? What we have to do, this IME region is bad, this is corrected, we will put a new good IME region and we will assemble it. So what we have done, we have IME region, here we click, we select the correct IME region, and we have a backup of correct IME region with us, right? So we just go here, IME region version 8, because this is Intel Series 7 chipset. So we just select and OK and build image, right? And after you build image, you will find it over here, output image. This is your correct BIOS file. So this is how to do an Intel IME region edit. And if you feel any problem, you can always send your BIOS backup to do Intel IME region edit. If you do not get to know the concept, you can send me for editing, and I will help you in this case. And I will also provide you all this software and backups to you for editing the Intel IME region. And thank you for this class. And in the next class, I'm going to cover the Intel Series 6 chipset and Intel Series 7 chipset, and we'll just finish up the theory portion, and we'll just stress all this data sheet that we have done theoretically via practically using CRO, right? So thank you for this class, and the next class will be very soon.
Okay, good afternoon everybody, and welcome to the class number 18 of laptop motherboard repairing class. In my previous class I had covered the Intel Series 5 chipset kind of board, and in this class I'm going to finish up with the Intel Series 6 chipset kind of board, and I will also show you some of the differences between the Intel Series 5 chipset and 6 chipset. And as I have already discussed in my previous class, that for analyzing any kind of board, what you have to do is just see the kind of Intel chipset that is present in the board, right? So if the board is Intel Series 6 chipset kind of board, then we have to download the Intel data sheet, that is Intel Series 6 chipset. And if your board is having like HM55 or HM57, then that is Intel Series 5 chipset. So you have to go through the data sheet of Intel Series 5. But here, since we already covered the Intel Series 5 chipset in this class, I'm going to cover the Intel Series 6 chipset. And what are the Intel Series 6 chipsets? Those are HM67, HM65, QM65, QM67, all kind of such chipset starting with 6 are Intel Series 6 chipset. And as I have covered in my previous class, that we don't have to go through the entire data sheet to analyze any kind of board. What is most important? Yes, the most important is electrical characteristics. And that too, in electrical characteristics, we had to just see the power sequencing and reset signal timing, because what we are interested in is how the board powers on. We are interested to know how the board powers on, right? Because what are the general faults in the motherboards? Either they are dead, or they do not start properly, or they restart after some time. So all these problems are related with the power sequencing. Alright, so let's go down over here in this page and let's see the power sequencing and reset signal timing of Intel Series 6 chipset. Okay, so here you can see the power management timing diagram is there, and our reference board is from the very start, from the very beginning, I'm taking the Intel Lenovo E47 board. Now, as you can see in this board, it is cover point, and we can see in my PowerPoint presentation, what is cover point? Cover point is Intel Series 6 chipset, which I have already mentioned, in this class. You can see, right? Intel Series 6 chipset are called cover point, and what kind of processor they support? They support Sandy Bridge. So our reference board is Lenovo E47, and we are today discussing the Intel Series 6 chipset timing diagram. Okay, and we go here. We had already covered all these slides. We had already covered those slides in my previous classes. We can just revise my previous classes before attending this class. Then that would be in sequence, right? That will be in sequence. So okay, so this is Intel Series 6 chipset. Now, one of the fundamental differences between Intel Series 6 chipset kind of board and Intel Series 5 kind of board is you don't find an extra clock generator. Yes, we do not see an extra clock generator. Here you can see there is no clock generator IC, right? There is no clock generator IC, and here you can see this Junitor, and we see there is no clock generator IC in an Intel Series 6 chipset kind of board, and you can see an extra clock 25 megahertz. There is 32.76 kilohertz. This is already present in Intel Series 5 chipset kind of board also, even in ICH also, but there is an extra crystal that is 25 megahertz and there is no clock generator IC. So this is one of the fundamental differences between an Intel Series 6 chipset kind of board and Intel Series 5 chipset kind of board, is that the clock generator work is already inside this PCH, and all the clocks are supplied via this crystal, 25 megahertz crystal. We can also see, in our previous, let's see the schematic diagram, the other kind of schematic diagram. Let's consider this R12, and here we will find there is a clock generator, right? This is Intel Series 5 chipset kind of board. There is just only one crystal, that is 32.768 kilohertz, that is for RTC section of this PCH, whereas in our Lenovo E47, which is Intel Series 6 chipset kind of board, we don't find any clock generator. Instead of clock generator, the clock generator work is totally done by the PCH, and the clocks are provided via this 25 megahertz. Okay, clock are provided via this 25 megahertz. Okay, another major differences between an HM67 kind of board and HM55 kind of board is an introduction of deep S4 S5. Earlier we have seen up to HM55 it was G3 mechanical off, then S5, then S4, then S3, then S0. But here there is one more kind of way, that is deep S4 S5. So here the energy is conserved up to one more level. So we can say HM67 kind of board are more energy efficient than HM55 kind of board, because here we can conserve energy. When the system is not working, we can conserve energy by going into another power wheel, right? So up till now we have discussed that how many kind of power wheel it is in the laptop motherboard: RTC wheel, suspend wheel, core wheel, right? RTC wheel, suspend wheel, and core wheel. But here in HM67 kind of board, there is one more introduction, that is deep sleep wheel. And what we call deep sleep wheel, it is deep S4 S5 wheel. As you can see here in the power management timing diagram, you can see after G3 it is deep S4 S5, whereas in HM55 kind of board you will find after G3 it is S5 and then S4. So there is one more power wheel that has been introduced in HM67 kind of board, and the laptop motherboard manufacturer can use this inherent facility, that is deep S4 S5. It depends on their policy. They may use it or they may not use it. They may use this deep S4 S5, or you can see here they may not use this deep S4 S5. So it totally depends on the manufacturer who is making the board based on HM67 kind of board. So in many kind of company you will find many kind of board by Toshiba, by HP, by Dell, by Acer. Some are using this deep S4 S5, some are not using this deep S4 S5. And how to know whether they are using it or not, we can see when we are analyzing the laptop motherboard, we can see whether they are using this deep S4 S5 or not. So the introduction of deep S4 S5 or deep sleep wheel, we can also call it as deep sleep wheel, is for energy conservation. You can conserve more energy. The board will be more energy efficient when they are using deep S4 S5, and we will discuss in greater detail about the deep S4 S5 in this class. So this is another major differences between the HM55 and the HM67 kind of board. One is there is no clock generator. The clock generator work is done by HM67. Second, there is one more introduction of a crystal in HM67, right? Earlier there are only 32 kilohertz crystal connected with PCH. Now there are two kind of crystal connected with the PCH. One is 32 kilohertz, another is 25 megahertz, right? And the 25 megahertz is for supplying all the clock in the motherboard through PCH, right? Through PCH. And what is the third difference? The third difference is there is an introduction of deep S4 S5 in the HM67 kind of board. You won't find this deep S4 S5 in earlier kind of board. And how does it help? It helps to make the board energy efficient. But when we introduce deep S4 S5, there is more signals, and we will study about these signals, right? So as usual, the very first step is VCC RTC. So in any kind of board, we'll just search VCC RTC, right? And always note, when I'm talking about the signal, when I'm talking about the signals over here, I mean these names to be inside PCH. That is, I mean this VCC RTC only inside PCH. I'm not talking about VCC RTC outside. So everything that is mentioned in the data sheet, they mean by this internal to the PCH. They mean by internal to the PCH, okay? So the very first step while checking this HM67 kind of board is to check the VCC RTC, okay? Now we have to check here by multimeter whether this plus 3V underscore RTC is coming or not, whether this plus 3V volt is coming or not. If it is not coming, now where we have to go? We have to search this plus 3V RTC. Obviously it would be coming from the battery, the RTC battery, but here we can search the plus 3V RTC, and you can see this plus 3V RTC, this plus 3V RTC is coming from the RTC battery, and another one from the plus 3V underscore DSW plus 3V PCA. Now this diode is an OR diode, right? In my book I have explained the use of this diode, whether that the application of diode is at many places. Here this diode is used as an OR diode. So or in OR diode, if this is true, then this is true. If this is not true but this is true, then this is true. That is, any one out of two inputs should be there to give an output, right? Any one of two inputs should be there to give one output. So this plus 3V RTC is coming from this RTC cell or from these two, plus 3V underscore DSW and plus 3V PCA. Now we'll check this plus 3V underscore. So if this plus 3V RTC is not coming, we have to check for this battery, or we have to check here, right? So, and sometimes also this battery connector is sorted, so this plus 3V RTC is not coming. So note this point, and I've already discussed this point in my earlier class. Now let's see this plus 3V underscore DSW. What is DSW? Deep sleep well, and this is called deep S4 S5 as well, and this is introduced only from HM67, not in HM55. You won't find this DSW in HM55. It has been introduced in HM67 kind of board, right? So note this point, and to explain this, now we will check these two signals from where these two voltages are coming, right? Because we have to trust the entire schematic diagram. So if this battery is there, then plus 3V RTC is coming. If this battery is not there, then these out of these two will give this plus 3V underscore RTC. Now we have to check from where these two kind of signals are coming, from plus 3V underscore DSW and plus 3V PCA. DSW means deep sleep well, deep sleep well. So let's search for plus 3V, plus 3V PCU. Obviously it will be coming from 3 5 voltage regulator. Once you start tracing the board according to the circuit diagram, then sometimes even you don't have circuit diagram, then you can easily know from where this volt would be coming. So where I have to check from where this signal is coming, where I have to check, right? You get enough idea to trace a board, right? So a very important thing that has come in HM67 is deep sleep well. So we'll learn about this deep sleep well. And also, one more thing is that there is no clock generator here in this kind of board. So when we trace the power sequence, we'll also talk that when does the PCH get to know that now I have to release clock, because earlier in HM55 kind of board you were having clock generator and the input of clock generator was CK power good, right? CK power good. So that signal goes to the clock generator that tells clock generator, okay, all the voltages are okay in the motherboard, so now you have to generate clock. But here in PCH, what tells to PCH that all voltages are okay, we'll see in the power sequence. So let's see plus 3V PCU. And you'll find it in our 3-5 volt regulator, right? Plus 3V underscore PCU. So now we find here, this is your, you can see in each page, this is your 3 volt 5 volt voltage regulator. Here you can see plus 3V PCU, and here you can see this is actually AC in DC, and this is charging, like this is charging. So plus 3 PCU. Okay, now this is our 3 volt 5 volt voltage regulator. You can see here with plus 5 PCU and plus 3 PCU is coming over here. Now this is 3 volt 5 volt regulator IC, and you can see this is EN1 and EN2, right? EN1 and EN2 is here. Now this EN1 and EN2 is tied up with 3V5 underscore EN, right? 3V5 underscore EN. Now from where this 3V5 underscore EN is there? 3V5 underscore EN, we search here. This is 3 volt 5 volt regulator IC, right? Okay, so now we'll see from where this plus 3V PCU and plus 3V underscore DSW is coming, right? So we'll just go and search the plus 3V PCU. Of course it is coming from the 5 volt voltage regulator, but we'll search in the schematic. Okay, so now this is the page. This is 3 volt 5 volt voltage regulator. From here we are getting the plus 3V PCU, and let's check this voltage regulator. In this you can see this is dual voltage regulator. It is generating 3 volt also from one side, and from here it is generating the 5 volt also. You can see this is 5 volt also, and so there would be two enable pins, EN1 and EN2. EN1 is for enabling this side of voltage regulator to generate the plus 5A PCU, and EN2 is for regulating this side of voltage regulator. And you can see, as we know, each voltage regulator has one LDO pin, and so when V in, the supply goes to the voltage regulator, the V in goes, and V in is coming from this. V in is coming over here. You can see V in register is coming over here. When V in comes over here, then LDO goes out, and this LDO output is 5V underscore L, and you can see this LDO is fed to the enable pin. This LDO, this 5V underscore L plus 3V 5V enable. So this LDO is enabling this voltage regulator and this side of voltage regulator. So while checking this voltage regulator, what we have to check, the first step is that whether V in input is coming or not, whether this V in via this resistor is providing the input voltage to this regulator or not. If it's there, second step is we have to check whether this voltage regulator is generating LDO or not, because if there is no LDO generated, then there would be no enable, and then this voltage regulator and this voltage regulator will not work, right? So if there is no LDO, then we have to check for the V in. If V in is there, no LDO is there, then you can simply change this IC. You can simply change this IC, right? You can simply change this IC. So this EN1 and EN2 is enabled by this LDO 5V underscore L. So once they get enabled, they will generate this volt. They will generate this volt plus 3V PCU, and checking the voltage regulator is same. We have already discussed how to check this top gate MOSFET, bottom gate MOSFET, this inductor, this capacitor. We need to check everywhere. Okay, so this plus 3V PCU is coming from this voltage regulator when it gets V in. Okay, when it gets V in. So when you connect adapter to the laptop motherboard, then V in would be generated. We have already discussed how V in is generated. V in would be generated, and then when after V in generation, this plus 3V PCU will be generated via this voltage regulator. Okay. Now the second thing is we go back to the plus 3V underscore RTC, alright, and you can see this is plus 3V underscore DSW. Now let's search from where this plus 3V underscore DSW is coming, alright. Wait. So how this plus 3V underscore DSW. Okay, so we have seen how this plus 3V PCU generated, and we can also see how this plus 3V underscore deep sleep well, this plus 3V underscore DSW is coming from here. You can see there are two sources for this plus 3V underscore DSW. One is plus 3V PCU and another is plus 3V underscore S5, right? So initially this plus 3V PCU is supplying the plus 3V underscore DSW. Now we go into our PowerPoint presentation and we see we just go to the, so after VCC RTC, the signal is RTC RTC reset, right? RTC reset. So we go and see the RTC reset. You find here the schematic RTC reset. This is for basically the resetting the RTC. Well, RTC reset and SRTC reset, we had already discussed all of this in our previous class, how this RTC reset is connected with RTC RST has. You can see over here, this is connected with RTC RST has. From where it is coming, you can see this is coming from the RTC battery. This is from RTC battery, right? So we have to check this capacitor and this sort pad. So if this is not there, then the RTC well will not start on, the PCH will not start on, your board will not start on. So we have to check this capacitor also. We have to check these two capacitors, right? So, and we go next. See, the Intel data sheet sometimes misses something. They miss some important things. And you see, after RTC RST has is directly going to VCC DSW3 but as we have seen in our earlier class also, the internal voltage regulator enable and deep sleep well voltage regulator enable, these two signal is also important. And you can see from here INTVRNEN, this will enable the internal voltage regulator. It will enable the internal voltage regulator of PCH. INT, and we had already discussed in our previous class also what does this mean, because this PCH has also internal voltage regulator for generating some voltages needed by the PCH, right? So this is connected with PCH underscore INVRMEN, right? And we can see here this is connected with plus 3 VRT underscore RTC. So right now we are talking about RTC well. We are talking about RTC well when you have connected the adapter to the notebook motherboard, or when the notebook is running on battery. Right now we are talking about RTC well. So what are the important signals in the RTC well? VCC RTC, RTC RST has, and INTVRMEN and deep sleep well VRMEN, DSW VRMEN. You can see here, you can search on this also, this one, because since this is introduced in only HM67, and DSW deep sleep well voltage regulator enable, and you can see where it is connected, DSW VRMEN. VREN. So this is M is not here. DSW VREN, and you can see this VREN is connected with plus 3V underscore RTC, is connected with plus 3V underscore RTC wire register, right? So this will enable the deep sleep well voltage regulator, those voltage regulator which will turn on only in deep sleep well. Now we'll talk about what is exactly deep sleep well, right? This deep sleep well is also called deep S4 and S5. Okay, so let us understand what is deep S4 S5. Since this is a new suspend well in HM67, in earlier kind of board we have seen there were RTC well, then you have suspend well, you have core well, right? This kind of well were there. And in the Intel ACPI we have already studied from G3 mechanical of S5, S4, S3, S0. But here in HM67 kind of board, here you can see just June, you can see after before S5 and S4 there is deep S4 S5. So in new ACPI, right, in earlier kind of board, in advanced configuration power interface, the power sequence was divided between G3 mechanical of, RTC section turns on, right? RTC section turns on, and after G3 mechanical off, it was S5, then it was S4, then it was S3, and then it was S0. But here in HM67 kind of board, a new ACPI is introduced, that is deep S4 S5. So let us understand what is deep S4 S5. Now this deep S4 S5 is related with the deep sleep well. Now let us understand this block diagram, because if we can understand this block diagram, then we are fully understanding what is deep sleep well, right? And what is deep sleep well turns on in deep S5, right? Deep sleep well turns on in deep S5. As you can see here, first the VCC RTC, so the RTC section turns on in G3 mechanical off. The deep sleep well turns on in the deep, you can see the deep sleep well DP power, okay, right? The deep sleep well turns on in deep S4 S5. So here in this block diagram we can see, and you can see this is PCH, and the PCH deep sleep well is powered by plus 3V underscore DSW. Now we can see over here plus 3V underscore DSW is driven by plus 3V PCU and plus 3V underscore S5. In the board where the deep sleep well is not supported, it is to be tied up with plus 3V underscore S5. That is, if deep sleep well is not supported, then that deep sleep well is same as S5, That's why it needs to be tied up with plus 3V underscore S5. So a HM67 board can be implemented in two ways. One, where the deep sleep well function is used, and in another where the deep sleep well function is not used. Where the deep sleep well is used, then it needs to be tied up with plus 3V PCU, and where it doesn't need to be used, it needs to be tied up with plus 3V S5, because in that case deep S4 S5 is same as S5, right? When this is not implemented, then deep S4 S5 is same as S5. So here you can see a use of diode as OR gate. You know, two diodes are used, and where there is only one output and two inputs are here, so it is to be used as OR gate. That is, anyone is high, then output will be high, right? Output will be high. Now as you can see in this board, plus 3V underscore DSW is driven by plus 3V PCU, right? So the plus 3V PCU is already in the board. We have already checked in the schematic diagram that plus 3V PCU has already been generated, right? Is already been generated, because we had covered until VCC RTC, RTC reset, and VCC DSW 3 underscore 3. This is the voltage for the deep sleep well. Now let us check in schematic diagram VCC DSW 3 underscore 3. 3 underscore 3. Now this VCC DSW 3 underscore 3 is for the deep sleep well, power for the deep sleep well, and as you can see, this is connected with the plus 3V underscore DSW. Now we will check from where this plus 3V underscore DSW is coming. Plus 3V underscore DSW is coming for plus 3 PCU, and this has already been generated, right? So the power has already come to the deep sleep well. Now in the schematic diagram we will see deep power, okay. Now the board will give a signal to the deep sleep well of PCH that power to the deep sleep well is okay. The power is already there, right? DPWR okay. Now we'll search DPWR okay. As you can see, DPWR okay is connected here. So since plus 3V PCU is there, so current will flow here, and as you can see, this is a transistor, right? As you can see, this is a transistor. This is NPN transistor. So at the base there is a current. So at the base there is a current. So it will allow a current from collector to emitter. It will allow a current from collector to emitter. So there would be a voltage drop across this resistor, and hence there would be 0 volt at this point. And as you can see, this is an N-channel MOSFET. As we know, in N-channel MOSFET, to turn on this MOSFET, the voltage at gate should be higher. Voltage at gate should be higher at the source, right? VGS should be higher. In N channel MOSFET, VGS should be higher. That is, voltage at gate should be higher from the voltage at source. But here you can see source is connected to the ground and voltage at gate is also 0. So this MOSFET is turned off. Since this MOSFET is turned off, this plus 3V PCU will go to DPWROK, and hence the deep sleep well gets deep power OK, deep sleep will power OK. So this plus 3V PCU will feed it to DPWROK. That will indicate to PCH that the deep sleep well has got power. That will indicate to the PCH that the deep sleep well has got its required power. Let us understand this once again. Here this plus 3V PCU is the power, right? This is forward bias, so the current will flow at the base. This is a NPN transistor, so when current is driven at the base, then current will flow from collector to emitter, and since current will flow from here collector to emitter, there will be a voltage drop, entire voltage drop across this resistor, because this is connected with the ground, right? This plus 3V PCU would be connected to the ground because base is activated, so entire voltage drop would be here. So this point would become 0 volt, hence the gate would become 0 volt. This is N channel MOSFET. You see arrow is inside. For N channel MOSFET, we always call this will be activated when VGS is greater than 0, that is voltage at gate should be greater than voltage at source. But here voltage at gate is 0 volt, voltage at source is 0 volt, so this MOSFET is turned off. So this plus 3V PCU is connected with deep sleep power OK, and hence the PCH gets 3 volt at deep sleep well power OK, and so that will indicate to the PCH that its deep sleep well power OK. Deep sleep well is active, it has got its power now. Okay, up till here is it clear? It has got its voltage, as well as the PCH has got indication that this section of PCH, the deep sleep well section of PCH has got its required voltage, right? Has got its required voltage. Now in a board which is implementing DPS5, what will PCH do? PCH will generate a signal sus1. And what is sus1? sus1 will indicate to ECH. This is sus1 hash, and as discussed in the previous class, all the signals in the schematic diagrams or by the Intel has been defined from turning off of a notebook motherboard, not turning on. So, but right now we are discussing how a notebook motherboard is turned on. So this sus1 signal at the EC will be high. That will this ECH will generate a signal to the EC sus1 to indicate to the EC that now you can enter into S5 stage. From deep S5 stage to S5 stage, the EC will then generate sus underscore SEK. That is, the EC will acknowledge this signal and it will generate back sus underscore SEK. And when the PCH gets this acknowledgement from the EC that yes, the embedded controller is ready to generate a signal to enter into the S5 stage, the PCH will generate SLP underscore sus, and this SLP underscore sus when it is generated to the EC will generate S5 underscore on, the EC will generate RSM reset. Earlier in HM55 this communication was missing because there was no deep S5. So in HM67 kind of board where deep S5 is implemented, we have to take into consideration these signals, because if S5 underscore on is not coming, it is not the fault of EC always. First it must get SLP sus, and when SLP sus would be generated by PCH, when it will get sus underscore ACK, and when EC will generate sus underscore ACK, when it will get sus1, and when PCH will generate sus1, when the deep sleep whale of PCH has got its voltage and got its power OK signal, right? So this concept was missing from Intel Series 5 chipset, and this is very important concept. This is very important concept. Let us go once again to the timing diagram. As we see, VCC RTC reset is there, that is in G3 state. VCC DSW 3 underscore 3 is connected by plus 3V underscore DSW, and plus 3V underscore DSW is fed by two types, plus 3V PCU and plus 3V underscore S5 in board where deep sleep pool is not integrated. This plus 3V underscore DSW is directly tied up with plus 3V underscore S5, whereas in a board where deep sleep pool is connected, this is fed by plus 3V PCU. So the voltage to this to the deep sleep well region is provided by plus 3V DSW, which is in turn provided by plus 3V PCU. Now it must get deep power OK. Since this voltage is here, this diode is forward bias, current will flow here, and this transistor will become active. This is NPN transistor, so this voltage drop would take place across this resistor. There will be 0 volt, this MOSFET gets turned off, so this plus 3V PCU is connected to the power OK. Now this deep sleep wheel has got its power, so PCH will give a signal to the EC embedded controller, that is in turn present in the IO controller, to signal to the EC that now we are ready to enter into the S2 stage. EC will acknowledge this sus1 signal that yes it is ready to enter into S5 stage. So sus ACK will be provided to the PCH, and PCH after getting this sus ACK will provide SLP underscore sus. After EC gets SLP underscore sus, S5 underscore on is generated, and you can check here plus 3V underscore S5 how plus 3V S5 is generated. Plus 3V S5 is generated, we can check here. This is very important concept, and this was missing from. If you don't know this, how this deep S5 is working, then in many problems you will just replace the IO controller, and perhaps the problem is from the PCH, right? Perhaps the problem is from the PCH. We'll check. So let's go find where this is provided. Yeah, now you can see this plus 3V underscore S5 is generated from the plus 3V PC. Let us zoom it to understand this, right? To understand. Now this S5 underscore on is generated from the IO controller. We can see there is nothing hidden over here. We just go to the page number 40, right? Or we can just search S5 underscore on, right? Now this S5 underscore on is generated from the IO controller, and when will IO controller generate this S5 on? As we can see, for turning on the IO controller needs three things: supply, reset clock, and supply is already provided by the plus 3V PCU. This is, you can see, plus 3V underscore EC, so it has already got supply. Then reset is there, we have already discussed reset, and clock is there. But S5 underscore on will be generated by the IO controller only when PCH generates sus1. Let us check sus1. SVSWARN has. You can see this is You can see this is PCH, and the sus1 signal is sus power ACK. So this will generate, this is going to the page number 40, that it is going to the IO controller. So you can see, you can see now we have to say sus power underscore ACK. This is going to the page number 40. Let me just search page number 40. Yeah, you can see the sus power ACK is going to the IO controller. So sus power ACK, which sus1 is going to the EC. Now the EC will generate sus underscore ACK. It will indicate to the PCL, yes, that we are now ready to enter the S5 state. So let us search sus underscore ACK, sus underscore ACK task. We go to page 8. Right, and you can see this sus ACK. Sus ACK is sus PWR ACK underscore R. Now from where this is coming? It must be coming from the IO controller, right? It must be coming from the IO controller. Yes, it must be coming from the IO controller. So this is in fact tied up with this sus ACK. So this is coming from the IO controller, and SLP underscore sus. After the IO controller gets SLP underscore sus, you see SLP underscore sus, SLP underscore sus. In this board, the deep S5 is not supported, so this SLP underscore sus is not connected. Where it is supported, this SLP underscore sus is connected with the EC, embedded controller, right? It is connected with the embedded controller. So in the board where deep S5 function is supported, that is in the board where SLP underscore sus is connected with the EC, only when the EC get SLP underscore sus, it will generate S5 underscore on. And you can see in page number 41, after the S5 underscore on comes, after S5 underscore on generates, it is fed to a transistor, and again this is an NPN transistor, and since this is an NPN transistor, when base is activated, then this collector emitter junction is activated, so this voltage will flow across this resistor, voltage will drop across this resistor. So this point is connected to this point. Since this terminal is not sorted, so voltage at this point is 0. Now since voltage at this point is 0, and this is an N-channel MOSFET, you see arrow is inside N-channel MOSFET. In N-channel MOSFET, this will be activated only when voltage at gate is higher than voltage at source, but here voltage at the gate is 0. After S5 underscore on comes, this voltage gets 0, this is 0, this MOSFET is turned off, so this 15 volt would get connected over here. Now this is again an N-channel MOSFET, gate is connected with 15 volt, voltage at gate is higher than voltage at source, so this MOSFET will turn on, and this plus 3V PCU will come at the source, drain to source. So this 3V underscore S5 is generated from this plus 3V PCU when this gate is activated. And when this gate is activated, when S5 underscore on come, this transistor gets activated, voltage drops takes place here, this MOSFET turns off, 15 volt reaches over here, voltage at gate is higher than voltage at source, this MOSFET turns on, and this plus 3V volt comes over here, right? So after S5 underscore on generates, now you can get plus 3V underscore S5, and similarly 5V underscore S5. So now in the board, this we have entered into the S5 state. stage. And how you entered S5 stage from the deep S5 stage? When S5 underscore on is generated, and when S5 underscore on is generated, when EC gets SLP underscore sus. When will PCH generate SLP underscore sus? When PCH will get sus underscore ACK. When will EC generate sus underscore ACK? When EC will get sus1. And when will PCH generate sus1? When its deep sleep well has got its power as well as power OK signal. So this is the concept of deep S5, right? This is the concept of deep S5. Now we'll go, we have already studied deep power OK, SLP underscore sus. Now we'll study what is how VCC sus. And as you can see in our previous class, VCC sus comprises of many suspend voltages, and we'll see how all suspend voltages are generated. After generation of all suspend voltages, then IO controller will generate RSM reset, right? You can see over here, after S5 underscore on, RSM reset is generated, and when RSM reset is generated by the IO controller, then that means all suspend wells have got its power. All suspend well have got its power, as we had discussed in the previous class. So now we'll check what VCC sus comprises of, right? What are the various voltages which are in the VCC sus?
Now we have already seen how deep S5 section is generated. Now we'll go to see how VCC sus is generated. After SLP sus, the S5 on has been released by the IO controller, and hence the motherboard has reached the S5 stage. So now the board will supply the VCC sus power to the PCH, but as we have seen, VCC sus includes three kind of voltages, and those three kind of voltages are VCC sus 3 V5REF sus and VSUS HDA. So let's see all of them. VCC sus 3 just go and search. And I can see this VCC sus, it should be inside PCH. Yes. Now you see VCC sus 3 is feeded by plus 3V underscore S5, and as we have seen that plus 3V S5 is generated from 3V PCU after S5 on is released by the IO. We'll see once again, plus 3V S5. And you can see this S5 underscore on, and as we have seen, this S5 underscore on is generated by the IO controller only when it gets SLP sus from the PCH. So this is the sus power for the PCH. As we have discussed in a previous class, this is the suspend power of VCC sus. Now another is V5REF sus. So we'll see where this is generated. V5REF sus, this is again connected with plus 5V underscore S5. So this is also being generated. Now we'll see VCC sus HDA. VCC sus HDA. VCC sus HDA is connected with plus 3V underscore S5. So this is also generated. So we'll go in the power sequence diagram. And after VCC sus, RSM reset. RSM reset will be generated by the IO controller. Okay, this RSM reset will be generated by the IO controller. Right, RSM, RST. You can see this is out from the IO controller. So when RSM reset will be generated by the IO controller has got supply, reset and clock. If the deep S5 section is enabled in the motherboard, it will wait for the sus1 signal from the PCH. After getting sus1, it will generate
After getting sus1, as you can see here in the diagram, after getting sus1 from the PCH, it will generate sus underscore ACK. After the EC gives sus ACK, PCH will generate SLP sus, and the EC will generate S5 underscore on first. This S5 underscore on, after generating, will generate plus 3VS5 and plus 5VS5, which will feed to the sus part of PCH. And after the PCH gets all these voltages, the EC, after power button pressing, will release RS and reset signal to the PCH. And as you can see, we are talking about RS and reset. So this, you can see this RS and reset. We are always talk about signal inside PCH. So you can see this RS and reset on the PCH is fed by the RS and reset from the IO controller. Alright. Okay, so we have covered up till RS and reset in the power sequence timing diagram for the Intel Series 6 chipset. And our next signal is sus clock. And what does sus clock mean? Sus clock means suspend clock. Actually, when the board is turning on, right now, when the sus clock is generated, there is no clock generator, that the clock generator has not turned on. As we have spoken earlier, the clock generator turns on in the last. But in S3 stage, what we call S3 stage as? S3 stage is called as suspend to RAM, right? That is, the context is saved in RAM. When your notebook motherboard is in S3 stage, the context is saved in RAM. But in S3 stage, the clock generator has not turned on. So who will provide the clock for RAM refresh? Because the RAM will save the context only when the RAM refresh takes place, and for the RAM refresh it needs clock. So who will provide the clock? At this point of time, the clock generator has not turned on. You can see the clock here is the clock 25 megahertz, but S3 stage is here. You can see S3 stage. At this point of time, the clock has not turned on. PCH is not providing the clock. So who will provide the clock to the RAM for refreshing the data? And this is a very crucial question. And for this sus clock is there. Sus clock is the key. Sus clock is the key, you know. In some kind of board, you will find sus clock to be connected to the RAM slot, whereas in some kind of board you won't find it as connected. But in those kind of board, the sus clock is internally connected to the PCH other pin. As you can see here in Lenovo E47, we go to the RAM slot, RAM 14, page number 14, and you see in page number 14 there is SMB run clock, SMB run data. So we search SMB run clock. Who is providing this clock? SMB run underscore CLK, and you can see this SMB run underscore CLK is provided by SMB PCH underscore CLK. So we go and find SMB PCH underscore CLK, and this is provided by the SM bus section of PCH. And as you can see, this SM bus section of PCH has been turned on by 3V underscore S5 voltage, right? By 3V underscore S5 voltage, and this SMB clock is internally connected with the sus clock, right? Is internally connected with the sus clock. So the PCH generates sus clock. Here you can see in this board, in this board, if you search sus clock, your sus clock is not connected. That is, sus clock is not connected to it is not connected to the motherboard, but whereas this sus clock is internally connected with the assembly section. So for RAM refresh, this SMB clock is needed, right? For RAM refresh, this SMB clock is needed. So you can see this, that sus clock is very important because the sus clock provides the clock for the RAM refresh, and this 202, this pin number 202 or DDR3 RAM is very important testing pin, right? Here this is a very important testing pin. This clock will turn on, there will be a clock present over here, there will be a clock present over here even before the motherboard has turned on, because this clock is provided by this sus clock, and you can see how this SMD run on this clock is connected with the sus clock. We once again check this CLK, and you can see this SMD run underscore clock is connected with SMD PCH clock, and you can see here this is SMD PCH clock is connected with the SMD clock, and as you can see this is fed by 3V underscore S5 voltages. That is, the 3 this section is turned on in the beginning. This section is turned on in the beginning. So the 208 pin number, we go back once again, right, and we just go to the page number 14 of RAM slot, that is the RAM slot pin, and you can see this page number 20, pin number 202 of DDR3 RAM is an excellent testing point for checking this sus clock. So this pin of RAM, 202 pin number of DDR3 RAM will have clock, and you can see the clock by oscilloscope. You put the probe, one probe, the positive probe over here and one to the ground, and you click auto on your oscilloscope, you will find a clock over here. If the clock is over here, that means your PCH has reached up to this stage, it has cleared this stage, right? So we can trust the notebook motherboard step by step. If we follow and understand this entire sequence, if we test the motherboard in this sequence, then you will certainly find the problem. So on the next, the next signal is SLP underscore S5. So let's check in a reference schematic diagram SLP underscore S5, and you can see over here, okay, there is gap, SLP underscore S5. You see over here SLP underscore S5 is not connected. This point I have already mentioned that in this board the S5 work is done by IO controller, because in this board the IO controller is generating S5 underscore on. In a board where the IO controller generate S5 underscore on or S5 enable, then this pin would be not connected, because the work of S5 enable is done either by PCH or by IO controller. In this board the work of S5 enable is done by IO controller, so that's why this SLP underscore S5 is not connected. Alright, so we go next, and the next signal is the PCH would generate our SLP underscore S4 and SLP underscore S3, and we can check over here after the PCH generate SLP underscore S4 and S3, all the various voltages would get turned on, because this SLP underscore S4 will enable the various voltage regulator, and you can see over here this is EM underscore SLP underscore S3. You can check this signal is going to various voltage regulator. You can see this is going to page number 40. This EM underscore SLP S4 is going to the IO controller, of course it will go to IO controller, and PM underscore SLPS3 will also go to the IO controller, and after that the IO controller will generate main on and sus on signal. Main on and sus on, you see main sus on is there, and similarly main on would be there. Two signal would be generated by the IO controller. You see main on and sus on. Main on and sus on, these two signals are generated, sus on and main on. These two signals are generated once the IO controller gets PM underscore SLPS4 and S3 from the PCH. Now you can see the sus on signal, sus on is going to the various voltage regulator. It is going to the page number 41 and 43. So let's go straight to page number 41, and you can see over here sus on, and you can see after this sus on is going to this transistor, and this is going to the base of this transistor. Since it is going to the base of this transistor, this transistor will turn on. This voltage would drop by this resistor, so there will be 0 volt over here. This is an N channel MOSFET, the gate is at 0 volt, this MOSFET is turned off, right? This MOSFET is turned off, right? This MOSFET is turned off. Okay, so now let's see how this PM underscore, as you seen, the PCH generates SLP underscore S4 and SLP underscore S3, and this SLP underscore S3 is fed to the IO controller. You can see over here. Wait, let's go back. And yes, you can see this SLP underscore S4 is fed to the IO controller, and then it will generate SLP S4 and SLP S3. It will generate sus on and it will generate main on, and this sus on and main on will enable all the voltage regulator to generate all the voltage in the notebook motherboard. You can see, let's see how this sus on and main on generate the other voltages, right? So the first stage is that this is the sus voltage regulator, that is 1.5 voltage regulator. You can see Vin is coming over here, Vin DDR is coming, and this 5 volt PC is already generated. So this is connected to the CS V5 in and V5 FLT, and a comparison, you see it has been connected to the comp pin of this regulator, so to compare whether this 5V PCU is there or not. And then you can see sus on is enabling drive high, drive low, and this MOSFET will switch on to generate 1.5 volt sus. So you can see how this sus on is enabling this regulator to generate the 1.5 volt sus. And to check this regulator, what things we need to check? First, we need to check whether Vin is there or not. Second, these all pins are connected with the 5V PCU, so we must check whether this 5V PCU is there, and obviously this will be there because these are already been generated. But you can see this is connected feedback. This is connected to the compare whether this 5V is there or not. So you need to check this capacitor also. In case this capacitor is faulty, then it will not give the correct comparison to this regulator, and hence the regulator will not work internally, and hence this drive high and drive low will not work properly, and hence this 1.5 volt sus won't come. So if we follow the sequence and if we know the correct working of any regulator, we can solve at least 95% problems, because all the problems on the notebook motherboard, most of the problems on the notebook motherboard are due to regulators or due to the components surrounding the regulator. So in this case, what we have seen is We know sus1 is generated by the IO controller, but to function this regulator properly, what things we need to check? We need to check this VIN, we need to check this plus 5V PCU, we need to check this comp pin, and then we need to check this drive high and drive low, that is these two MOSFETs, and if these two MOSFETs work, then 1.5 volt sus would come. Let's see another voltage regulator. Let's see how the main on is generating the voltages, right? Main on is generating the voltage, and you can see the main on is working in three modes. One is for the PWM IC and it generates 1.05 volt underscore PCH plus 0.85 volt VGPU, and second is that it is also enabling some linear regulator power supply to generate these two voltages, and again it is also inducing plus 3V plus 5V. So let's check all of them. Here this main on, you can see the main on. Here you can see this 3V PCU and 5V PCU would get converted to plus 3V and plus 5V with the help of main on, and you can see here the main on is going to the base of this transistor. Current will flow from collector to emitter, so ground, this point would be connected to the ground, voltage would drop here, so the voltage at the gate is 0, so this is N-channel MOSFET, this MOSFET will turn off and this 15 volt would reach to the gate. Since this is N-channel MOSFET, voltage at gate is more than voltage at source, so this MOSFET will get enabled and this plus 3V PCU is connected to the plus 3V volt. Let's see once again. You can see this plus 3V PCU is going to the drain of this MOSFET. Main on is going, enabling this transistor. This is turned off because here it is connected to ground. Gate and source both are connected to ground, so this 15 volt is getting connected to the gate. This will enable this MOSFET, and this 3V PCU is connected to the plus 3V volt. So you can see the working of main on. Let's go to the next slide. And here in this slide, the 1.8 volt is generated from plus 3V PCU with the help of main on, and let's see how this voltage regulator works on. And you can see this 3V PCU is connected to the VIN pin of this voltage regulator. Second, enable is coming over here, and the PS, this is a linear voltage regulator. So linear voltage regulator, you can see it will linearly produce 1.8 volt. While you can see the one is feedback V sense, so it will iteratively generate 1.8 volt. That is, this regulator will check the output volt, whether the output volt is 1.8 volt or not, and how it will check. You see there is a feedback given to this linear regulator, so it will iterate, it will increase the output to 1.8 volt. If the voltage is not 1.8 volt, it will iterate, so finally 1.8 volt would come over here, 1.8 volt would come over here, and we must check these two registers. These two registers are very essential because this is a linear regulator. You see there are no MOSFETs over here, no MOSFETs over here. It is generating 1.8 volt from 3V PCU with main on as enabled by checking. You see, by checking, one, the output is connected to the input via these registers, so we must check this resistance value, and according to this R1 and R2, this output is changed, and you can see the value of Vout is 0.8 into R1 plus R2 by R2, right? So if we change this R1 and R2, we can change this output volt. This is a linear voltage regulator, and we must check these two registers. let's and after generating 1.8 volt, it will generate hardware power good, right? Hardware power good, and we can see all the power good is connected. All the power good is connected. That is, power good of all voltage regulator is connected and feeded back to the IO, feeded back to the IO controller to inform the IO controller that yes, all voltage regulator has turned on. Let's see another voltage regulator, that is to generate 0.85 volt. This is 0.85 volt voltage regulator, and you can see this V in is input, V in is the input, and the next is 5 PCU is feeding to the rest of the VDDA and DST. So we need to check two things, VIN and 5 PCU as input and another main input as main on. You can see main on is coming, so it will generate drive high and drive high, drive high and drive low, and this will switch this MOSFET. You can see this will switch this MOSFET to generate the 0.85 volt. So main on and sus on are enabling all the voltage regulator on the notebook motherboard to generate the rest of the voltages, right? To generate, and again you can see this is also generating hardware power good. You can see all the hardware power good are connected to generate one hardware power good. In this motherboard, around 27 kind of voltages are there, right? But the important power good are connected, important power good are connected at hardware power good, and you can see this hardware power good is fed to the IO controller to generate VRON. You can see this hardware power good is feeding to the IO controller and it generates the VRON and EC power OK after delay of 99 milliseconds. That is when we are on. Let's check this. This is very important. This hardware power good is connected. You can see, let's go back. This hardware power good is connected with all the hardware power good of important voltage regulator. And what are the important voltage regulator? Plus 3V PCU, that is 3 volt 5 volt voltage regulator, 1.5 voltage regulator. This is for RAM 1.05 voltage plus 0.85 plus 1.8 vGPU core plus 1.1 volt GPU to generate the hardware power good, and this hardware power good is fed to the IO controller. It will generate VRON, and after a delay of 199 millisecond, EC power OK generated. Let's see where this VRON is coming or is going. Obviously this VRON is going to the CPU core voltage regulator, right? CPU core voltage regulator. This is the CPU core voltage regulator, and you can see this VIN is the input, right? This plus 5 volt is fed to the VDD. We need to check these two are coming to the voltage regulator or not, the core voltage regulator or not. Third is this 5 volt at both pins, and the fourth is here, the plus 5 volts should be here. The fifth is SVID alert and data, and clock. This is very important. This is very important. Let's discuss this when we reach this stage in our discussion in the data sheet of HM67, right? So up till here we have discussed how this VRON is generated and hardware power good is fed to the IO controller. VRON is generated, EC power OK is generated, and let's see the working of this core voltage regulator, because this is very important. Once we reach here in our data sheet, so in our data sheet we have covered SLP underscore S5, S4, S3, and we have seen the implication of the generation, how this SLP S1, S3 opens up all the voltage regulators, right? The next is SLP underscore A. This is very important. This SLP underscore A is 4. This is 4. We can see over here this is 4. Let's see the definition of SLP underscore A, because let's go in our presentation for this class. I have mentioned a very important points. We must always correlate the various kind of board to analyze, because it's not written everything explicitly in the data sheet. What you have to do, you have to analyze and you have to find out, because in data sheet everything is there, but some are implicit meanings, right? So we have to correlate. Let's go, and you can see SLP underscore A. Yes. Good. Yeah. So there is the difference between HM67 and HM55 is that the SLP underscore M has been renamed as SLP underscore A. That is, SLP underscore A is to enable the any section of PCH, right? It is to enable the any section of PCH. Let's search over here the definition of SLP underscore A. Please note we are at page number 351, so we need to go back to 351 once we see the definition of SLP underscore A. Let's check the definition of SLP underscore A. We go back to page number 1 and we search SLP underscore A. You can see this SLP underscore A is used to control power to the active sleep well PCH. Active sleep well PCH. This is important. This active sleep well is basically the AMI well. In Intel Series 5 chipset, we were talking of AMI, but here this AMI well is renamed as active sleep well, and you can see here, we have written as VCC-AMI is renamed as VCC-ASW. That is, the voltage for the AMI has renamed as VCC-ASW. SLP underscore M has renamed as SLP underscore A. So we can see, let's go back to the page number 353 and 351, I think. Yeah. So you can see this SLP underscore A is for generating this voltage VCC-ASW. And what is this VCC-ASW? This is the voltage for the active sleep well, and in Intel Series 5 chipset, this VCC-ASW was basically the AMI power, the voltage for the AMI region of PCH, the voltage for the AMI region of PCH, right? Let's check this SLP underscore A in our schematic diagram. And this SLP underscore A is not connected. Why it is not connected? We need to ask question why it is not connected. Let's check VCC-ASW. From where this VCC-ASW is fed. We search over here VCC-ASW, and you can see this VCC-ASW, that is the active sleep well, that is the AMI inside the PCH. The power to the AMI inside PCH is fed by 1.05 volt underscore PCH, and this volt is already been generated by neon. You see, plus 1.05 underscore PCH. Let's check from where this is coming. 1.05 plus 1.05 volt, 1.05 volt underscore PCH. Let's see from where it is coming, right? From which voltage regulator it's coming. Okay, so you can see this voltage regulators, this voltage regulator is generating 1.05 volt underscore PCH, and you can see the enable of this voltage regulator is connected with main on, and you can see here the main on has already been generated, because this after the IO controller gets SLPS2 and SLPS3, the IO controller has already generated sus on and main on, and when sus on and main on is generated, this VCC ASW is automatically generated, so there is no need of SLP underscore A. So you can see the IO and PCH together work to control the power sequence, right? Some part of the function of PCH is done by IO controller during power on, right? So IO controller and PCH both are important in turning on of the laptop motherboard. Here this SLP underscore A is not connected, so the voltage VCC ASW is feeded by plus 1.05 volt underscore PCH, which is generated by a voltage regulator which is enabled by main on, and this main on is coming from IO controller when the IO controller gets SLPS4 and SLPS3. So this VCC ASW, let's go back. VCC ASW is for the active sleep well, that is for the any reason, and we'll talk about the any reason of Intel Series 6 chipset, and we'll see how it is different, how it is little bit different from the Intel Series 5 chipset, right? So this VCC ASW is generated. Now the board will provide VCC supply, and what are VCC supply? We have seen earlier the VCC, you go to the top and you see VCC, right? VCC includes VCC IO, VCC core, VCC3 underscore 3, and you can see these voltages are already being generated because the IO controller has provided main on and sus on. Let's check one of them. We go to search VCC core in our data sheet. And you can see this VCC core is connected with plus 1.05 volt underscore PCH. We have seen earlier this is provided by an voltage regulator which is enabled by main on signal, right? So similarly, all these voltage would be generated, right? After these all voltage are generated, we have seen that this IO controller generates VR on, and VR on is going to the core voltage regulators, and you can see there is a very important point we have discussed in earlier class also, that in Intel Series 6 chipset kind of board, the processor must be inserted in the notebook motherboard to turn on this notebook motherboard, whereas in board having double bridge technology like north bridge and south bridge, we can turn on the notebook motherboard even without putting processor. This was a major difference, because here the processor is providing the SVID data to the core voltage regulator. Let's go back to our presentation and we will see this is very important feature. Go to the next slides. We already discussed all of them, and you can go through this PPT to understand each things again and again, right? Let's check. Yes. Yeah, so you can see this, all all hardware power grid is fed to the IO controller. You see, this hardware power grid is fed to the IO controller. It generates VRON. This VRON is going to the core CPU core voltage regulator, and after 99 millisecond, this EC power okay generated. We have already talked why 99 millisecond delay. Let's check VRON. Where is VRON going? VRON is going to the core voltage regulator, and you can see what are the important things to be considered. We are discussing only class on VRM, how the voltage regulator module operate. Here VIN is one of the important input. Second is VDD and VDDP. VDD and VDDP you can see, and this L gate, and the CPU will provide this data, alert, data and clock, and then this VRON is coming over here, VRON is coming over here, and then you can see this drive high and drive low will turn on, switch on these MOSFETs to generate VCC code, right? To generate VCC code. So we have seen that in this board, in Intel Series 6 chipset, the processor must be inserted in the notebook motherboard to generate the core voltage regulator. Because if processor is not inserted, then these three data will not be provided. These are the default data, right? At this point of time, the core voltage, the core wheel of processor has not turned on. Core wheel of processor is also having many wheels. The processor 1.5 volt section of processor has already been turned on, right? 1.5 volt section you can see over here. Let's go in the data sheet to clarify this, right? To clarify this, here 4, 5, 6, 7, you see this processor is connected with the RAM, and RAM turns on before the processor turns on, because the 1.5 volt section of this processor has already been powered on. You can see over here, we go to the page number 6, and you can see what are the various voltage required by this processor. Plus 1.05 volt underscore PCH. This has already been generated before the core voltage. This has already been generated before the core voltages. So this VRON, you can see here, this SVID alert, data and clock is provided by the processor to the core voltage regulator. After getting this data from the CPU, it will calibrate, this voltage regulator will calibrate and will generate proper core voltage, that is VCC core. And you can see here, you can see over here in the power sequence, CPU is providing the CPU SVID, and then VCC core CPU generated. After this VCC core CPU generated, it will provide IMVP power grid. You see the power grid is connected with the IMVP power grid, and the IMVP power grid and EC power OK are together ended, and that's why this EC power OK is generated by the IO controller after a delay of 99 millisecond, because during that time of 99 millisecond, this IMVP power would be generated, and both will be ended together to generate sys power OK. And in next slide you can see, how this sys power OK is important to generate the termination voltage of RAM. The termination voltage of RAM. Let's go to the slide. So this is very important. We need to revise this thing, right? You can revise this PowerPoint presentation. This is a very important PowerPoint presentation. and everything. That, yes, you can see over here V in is coming, right? And VDDP and VDD and VDDP has got its voltage. Plus 5 is connected with the L gate, and SVID data from the processor is coming over here. VR on is here, VR on, okay, and then this CPU will drive high, this regulator will generate drive high and drive low to switch these MOSFETs to generate the VCC core. After the VCC core is generated, it will generate IMVP power good. You see IMVP power good, and this IMVP power good is fed to this AND gate, and EC power okay and IMVP power good both are ANDed together to generate the sys power okay, that is system power okay. And you can see over here this is for generating the termination volt. This sys power okay is connected with the S3 pin, and then this linear voltage regulator will generate plus 0.75 volt DDR underscore VTT, that is termination voltage. That is the termination voltage is generated after the core voltage, right? After it is generating the core voltage, because sys power okay is generated. Sys power okay is generated by IMVP power good. IMVP power good is generated by the core voltage regulator. Once the CPU gets proper core voltage, then power good is generated. This power good is ANDed with the EC power okay to generate the system power okay. This system power okay is fed to this voltage regulator to generate the termination volt. This plus 0.75 volt is the termination voltage, and you can see here in this diagram EC power okay is fed to the power okay of the PCH also, right? Is fed to the power okay of PCH also, and sys power okay is fed to the sys power okay of PCH also. And after, you can see, right, these are fed, and then this PCH will generate PLT reset, right? This will generate a PLT reset, and this is very important. The PLT reset would be generated by the PCH, and that would go to the CPU, right? That would go to the CPU to reset the CPU. To reset the CPU. Let's check once again. Here the IMVP power good is provided by the voltage regulator. IMVP power okay and EC power okay are both combined to provide sys power okay. This sys power okay has one very important function, that is it will enable this voltage regulator to generate the termination voltages, and after the CPU gets termination voltages, this EC power okay and the sys power okay will be fed to the PCH, and the PCH will release DRAM power okay, that is the power good, that is the power to the RAM controller inside PCH. The memory controller inside PCH is okay, right? Is okay. Then this PCH will generate DRAM power good, and where this DRAM power good is going? DRAM power good is going over here. You can see DRAM power good, and after that the PCH will generate PLT reset, and this PLT reset is fed to an AND gate and then connected to reset this CPU, because at this point CPU has got everything, and then the CPU will read BIOS. So let's see in our data sheet once again. We have seen VCC core CPU generated, sys power okay generated, and power okay and AP power okay. Power okay and AP power okay is fed to the PCH. We can go here, power okay, PWR okay. This PWR okay is fed by the EC power okay, right? So this EC power okay is feeding to the PCH, and after the PCH gives power okay and PWR okay, PCH will generate DRAM power. Okay, you can see over here the PCH will generate DRAM power. Okay, you can see DRAM power. Okay, and you can see this DRAM power. Okay, is connected with PM DRAM power board. So this is provided by the PCH, right? This is provided by the PCH. PCH to CPU DRAM power. Okay, so once the CPU gets DRAM power, okay, then the board will have its clock. Let's see how this clock generation and this DRAM power, okay, is related. Okay, so now DRAM power, okay, is generated by PCH to CPU. So now the PCH will generate, that is PCH will output clock. First the board will supply 25 megahertz input to the PCH, and the PCH will then output the clocks to all the part of main board. But how does the PCH understand at this point that I have to generate clock? What is the logic behind it? What is the logic behind it? And we can see the clock generation is closely related with the AP power, okay, that is active will power, okay, which is also the AV power, okay, because in Intel Series 5 chipset this was AV power, okay. In Intel Series 6 chipset it has not remained as AP power, okay. For this, let's go and see the AV version of Intel Series 6 chipset. And as I have spoken earlier, that this is Intel Series 6 chipset, so this would have Intel AV7 series. In Intel Series 5 chipset, the AV version is 6. In Intel Series 6 chipset, the AV version is 7. In Intel Series 7 chipset, AV version is 8. This is Intel Series 6 chipset, and you can see the entire booting of this AV region, right? Booting of AV region. The first step is that the PCH will load default clock, okay. The PCH will load default clock because a crystal has been connected over here, right? A crystal is already connected with the PCH, so the PCH will generate the default clock. The second stage is that the AV inside the PCH will turn on. When the AV inside PCH will turn on, when AP power, okay, when the board will provide AP power, okay, to PCH, that is active will power, okay. When active will power, okay, is provided to the AV of the PCH, the AV region will turn on. It will read the AV from there, and the clock is loaded in the internal clock controller register. What does ICC stands for? Internal clock controller register. And then this data will be fed to the internal clock hardware of PCH, and then the PCH will output clocks to the platform. So you can see this is the correct step. What is the first step? Since a crystal is connected with the PCH, PCH will generate the default clock. Second step is that when AP power, okay, when the board will provide AP power, okay, the Intel AV inside PCH will turn on, and it will exchange data with the AV firmware, and this AV firmware will populate the internal clock register inside PCH, and then this data will be shifted to the clock hardware, and hence the PCH will generate clocks to the all the motherboard. So you can see how AV is crucial, right? So let's go to the next page. Okay, so the board will generate clock. We go to see the Intel Series 6 chipset, how clock is generated. Let's see first 25 megahertz. And you can see the PCH is connected with the 25 megahertz, and you can see the PCH is generating all the clocks to the motherboard, also generating the clock for the CPU, that is BCLKM, BCLKP. You can see where this is going. CPU, CLK, CLK underscore CPU underscore BCLKN. Let's check. And this is going to the page number 4. This is going to the page number 4. You can see it is feeding the clock to the CPU. It is feeding the clock to the PC, to the CPU. And the next thing is PCH will generate proc power good. Proc power good. See, this is very important. You can see over here at this stage, the CPU had generated, the core voltage is been generated over here after we are on. After we are on, you can see over here in this, we need to understand this very well. We are on, and this we are on is over here, and you can see this VR on has been generated by the IO controller, and here the SVID alert data and clock. Initially when the CPU is connected to the socket, the core part of CPU is not turned on, but this VID data, this is the default VID data. Initially the CPU will provide the default VID data, and then this clock generator will generate the VCC core, right? VCC core. When this VCC core is generated, the core part of CPU is turned on, right? Core part of CPU is turned on. Now, core part of CPU is turned on, that is, it has got supply. Second thing is that here you will get, here this will get, crystal clock BCLK P and N, right? It has got, the core part has got supply, and it has got clock also. From here, clock also. Now the CPU, you can see set VID load. After the PCH will provide proc power good. You can see over here, after the CPU will provide processor power good, then this VID is loaded. You can see over here, after this PCH provide proc power good. Let's check first proc power good. PROC proc power good, and you can see this proc power good. And when will the PCH generate proc power good? When the clock has been generated. Everywhere there is a clock, then this PCH will generate proc power good, and you can see this proc power good is where it is going, H power good. This is going to the CPU. You can see H power good is feeded to the CPU section, right? It has been fed to the CPU section. And when this happens when the clock has been generated, right? So at this point of time, the CPU has got supply, it has got clock, and now it needs reset in order to read data from RAM, in order to start booting from BIOS, right? At this point of time, the CPU has got supply, it has got clock, and now what it needs reset. In between these two stages, the PCH will generate sus_stat, which we had discussed in earlier class also. Here in this schematic, it is not connected, it has been not used. You can see over here, this is not connected, okay? And after this, there is a thermal trip. You can slowly zoom it over here and zoom it. Sus_stat is not used, and you can see thermal trip will work when both PCH will generate power good, and you can see the CPU will provide thermal trip, and here the thermal trip value would be high when it is turning on, and thermal trip value would be 0 when it is turning off. You can see over here thermal trip, THRN TRIP, and you can see thermal PC. The CPU is generating thermal trip. Here you can see PCH is generating PM underscore THRM TRIP. This is generated by the CPU, and when it will be generated by the CPU, when the CPU has got processor power good, that states to PCH that CPU is in correct condition to receive reset, right? This indicates to PCH that now the CPU is ready to receive reset, and after that PCH will generate PLT reset, and PLT reset will reset the processor. You can see PLT reset. You have to search inside PCH. PLT reset, and this is, you can see PLT reset is connected with the PCI underscore PLT reset hash, and you can see this PCI underscore PLT reset is ANDed with an AND gate to generate PLT reset hash, and you can see PLT reset hash, where this is going PLT reset hash. This is going everywhere to reset the platform, and we have to check to the CPU. You can see this PLT reset is connected with a reset enough processor, and hence processor will reset, and now the PCH and the CPU will communicate via DMI, and via DMI they will exchange data via DMI. So this is very important. The thermal trip signal from CPU to the PCH will indicate to the PCH that the CPU is now ready to receive reset, and after that the PCH will provide PLT reset, and hence the CPU will start communicating with PCH to read the BIOS data and then start booting. We will discuss how this booting function works in my next class, but meanwhile we already finished with all the theoretical portion, so I will start with practical. I will show all of the signals flow via oscilloscope, and for this you can see I have already prepared the, you can see Intel HM67 timing by oscilloscope. Like using oscilloscope, when you are using oscilloscope, you must learn to compare signals. That is, if you are having a dual channel oscilloscope, you must use both channel of oscilloscope to compare signals, to compare two neighboring signals. Like this, I have compared power button hash and RSM reset, and you can see I have compared RSM reset and power button out, and you can see I have compared these two. So I will show you how to use oscilloscope to trace all the power sequence. So I'm finished with the entire concept of power sequence, and in my next class I'm going to use oscilloscope to show you how this power sequence traces and how easily you can find problems. I will also show you the use of DC power supply, and also how to convert a graphic board into a non-graphic board, and a practical on some very basic fault finding scenario, right? Some very basic fault finding scenario, like how to test the exact sequence in testing when your motherboard is completely dead. Of course, I have been teaching you this is the correct sequence to test. Now I will show you this via oscilloscope. All these signals via oscilloscope or by multimeter I will show you. Now I'm finished up with the theory, so I request you to revise all these things before we go to the next class, because in the next class I'm going to just show you the values via oscilloscope. I'm not going to explain you what is this signal name. You need to refer the Intel Series 5 chipset, Intel Series 6 chipset, and also ICH9. And we can try to analyze the Intel Series 7 chipset timing diagram, which is almost similar to this Intel Series 6 chipset. You can do it yourself, and if you have any confusion while tracing the Intel Series 7 chipset, you can always contact me. Okay, thank you.
We are going to cover everything that we have covered till now in theory. I have already explained the power sequence of ICH and PCH. So in this class I will show you everything practically. And I have taken one board, that is Dell 1545, and I have a schematic of this also, Dell 1545. So you can open the schematic. You can see over here. Right now you can see this board is in completely dead condition because it has no power source. You can see there is no adapter connector, and you can see there is no RTC cell over here. So I will insert the RTC battery and I will show you the power sequence. And this is the schematic diagram of Dell 1545. In the schematic diagram you can see the ICH is ICH9, and as I have already discussed in previous class, that power sequence is controlled by this chipset. So we'll open up the data sheet of ICH9, and you can see here is the data sheet of ICH9, and the complete power sequence timing diagram is explained over here. So the very first signal is VCC RTC. So we'll check for the VCC RTC in this circuit diagram, and type over here VCC RTC, and you can see this VCC RTC is fed by RTC underscore cell. So we'll check from where this power supply is coming. RTC underscore cell, and you can see this RTC underscore cell. There are two sources for this one. One is 3.3 volt and another is the battery connector. Right now our motherboard is not connected to adapter, so the source for this RTC underscore cell would be this battery. So I will show over here whether this is coming or not. So let's check over here in this motherboard for the RTC underscore cell. If this volt is not coming, that means this diode is faulty, or this resistor is faulty, or this battery is short. This battery is not having the charge. So we'll look for the signals over here. And you can see 3 volt is coming over here, and let's check it on the diode also on U24, and you can find that U24 is on the back side of this board. So this is the diode U24. So we have to check for this diode. If this RTC underscore cell is not coming, then we have to check this U24 diode, and we have to check for this battery. Okay, so here this diode is okay, and then we go to the next step. The next step now will give power to this board. Now we'll give power to this board via this DC power supply. As I have already told you that very basic equipment for repairing your cook motherboard is DC power supply, oscilloscope, and a very good multimeter and one BGA. Okay, this board, and now we'll see. We'll check for this one. This plus 3.3 volt underscore RTC underscore LDO. And this diode is basically OR diode. You can call it as OR diode. Diode can be connected in two ways, one in OR and another is in AND, and I will show you the application of AND diode also. Here is that if any one input is coming, then it will give you output. That is, if this is 1, then this output will come. If this is 1, then the output will come. So this is basically OR diode. So now we check for plus 3.3. Suppose your RTC battery is dead, but if it is connected to the adapter, then this will give output. So we'll check for the plus 3.3 volt underscore RTC underscore LDO. From where this is coming. And you can see this is a small IC. Small IC U19, the VIN is connected to plus 5V ALW2, and enable is also connected to this, and this is giving you output. So if this is not coming, we have to check for this capacitor, and we have to check for this IC, we have to check for the input of this IC, that is plus 5V ALW2, and we will check from where this is coming. U19, we can find this IC into the board where U19 is. You can see this is circuit diagram, it is written -1 because right now we had given power to the notebook by adapter. So if you have not connected adapter, then this sequence is not at all required. We'll go back to see once again. Yes, you can see over here, this RTC underscore cell is provided by one of the two inputs. So if we have not connected adapter, then that sequence we need not require to trace. So that's why it is written -1 over there. We'll go back to find. So you can see it's written -1. That is one step behind this step. So here we'll check the inputs, we'll check the enable, and we'll check the outputs. So let's check this U19 IC. U19 is a 5-way IC, and you can see the input is connected to plus 5 volt. So we have to find plus whether 5 volt is over here or not, and enable is also 5 volt ALW2. So we have to check at pin number 1 and 3, it should have 5 volt. So let's check over here on multimeter. This is pin number 1, and you can see this is close to 5 volt, and enable pin number 3, and on pin number 3 also you can see this is 5 volt. So the inputs are okay, and let's check on the pin number 5. The pin number 5 will give you 3.3 volt. Pin number 5, you can see 3.26. So this is 3.3 volt. So 5 volt is converted to 3.3 volt via this IC. So if 3.3 volt is not coming, we have to check for the inputs, and if the inputs are not coming, then we have to check from where this plus 5 volt ALW2 is coming. So let's check from where it is coming. see this 5 volt ALW2 is LDO output of this IC. Is LDO output of 3 volt 5 volt regulator IC. And if this LDO is not coming, then we have to check whether this IC is receiving its proper input or not. And this is max 1702 U18. So now in the board we'll find where U18 is and we'll check for this volt 5V always 5V underscore ALW2. So this is 3 volt 5 volt regulator IC, and you can see this is a dual regulator. One side it is generating the 3.3 volt and another side it is generating the 5 volt. And we have to check this 5 volt is LDO output of this IC. So we have to check the pin number 7 of this IC, the U18. So let's check whether this pin number 7 is having 5 volt or not. Pin number 7, LDO. This is LDO output of 3 volt 5 volt regulator IC. And you can see so we have to check this 5 volt always. This is the LDO output of this IC, and so we'll check the output at pin number 6, pin number 7 in fact, but never check voltage at this pin. You can check voltage at the components which is connected with this pin. Like here, we can check voltage over here, over this capacitor. If you have to check the output, LDO output, you can check whether this capacitor is having that voltage or not. Because when you are checking voltage at the pins, there might be problems that it may get sorted. So always check voltage at the related components. So you check at this capacitor to find whether the 5 volt is coming or not. This is the LDO output, and you can see this is 4.92 volt, which is 5 volt. And if this 5 volt is not coming, we have to check the inputs of this IC. The inputs is VCC and in, that is pin number 6 and pin number 3. So we can check the voltage at pin number 3 and pin number 6, whether the voltages are coming or not. And you can see at pin number 6, this is feeder by PWR underscore SRC 17020. So let's find out what is the voltage value at pin number 6 and pin number 3. Always check voltage at related components. And if you want to check voltage, then you have to do it very cautiously. So you can see this is coming to be 20.32. This is the adapter voltage. Let's check what is this PWR underscore SRC is coming. You can see you can see in the DC power supply, this is the adapter voltage. And you can also check in schematic diagram if this 20 volt is not coming. In case this 20 volt is not coming, so we have to check from where this 20 volt has reached over here. So we can check over here PWR SRC 17020. See, this is PWR SRC is converted into PWR SRC 17020. So we have to check for. So you can see this is the page where PWR SRC, and this is connected via the DC in. Basically, this board have one daughter board from where this DC in is coming, and you can see this is a P-channel MOSFET, double port GSM. You can see this arrow is outside, so this is P-channel MOSFET. But we have already discussed that in P-channel MOSFET, if input is connected to the drain, then it will act like a diode, not as a MOSFET. So this voltage would get simply passed across this diode over here, and this DC in S becomes PWR SRC. So this is the adapter volt 20 volts and this is 20 volts. So if this PWR SRC is not coming, we have to check for this resistor and we have to check for this MOSFET. If these two are faulty, then you won't get PWR SRC. So let's go back to our 3 volt or 5 volt regulator IC. We have to check for the VCC also, VCC pin. Okay, so we had already checked this PWR SRC 17020, how it is generated. So if LDO is not coming, you have to check two things, that is IN and VCC. This VCC at pin number 3, you can see this is supplied by plus 5V underscore VCC1, that is plus 5 volt should come over here at VCC, and this plus 5V VCC1 is being converted via this resistor from plus 5 volt. And you can see a very important thing is being written over here. No install for ISL 6236, install 10M for MAX 8778. And here you can see this 3V 5 volt regulator is 17020E. That is, you can use these two voltage regulator in place of this voltage regulator. But while you are using ISL 6236, you don't require this resistor, and if you are using MAX 8778, then you have to install a 10 ohm resistor over here. This is a very important point written over here. So we have already checked. यहाँ पे stop. यहाँ पे गड़बड़ है. A very important thing. पता है सर, एक मिनट. So we have checked this IN and VCC. In this board you can see this VCC is actually connected with this 5 volt ALW2. So the only one thing that you have to check is IN, and you can also check this on LDO. There is one special signal inside this IC. When this fourth number gets this voltage, this 3.3 volt underscore RTC, then this LDO will give output 5 volt. So what are the steps? The first step is that this IC gets the V in, then this IC will generate RTC volt 3.3 volt, then this 3.3 volt will be fed to the enable LDO, that is on LDO. When this on LDO gets 3.3 volt, then this IC will generate LDO of 5 volt. So let's go back to our page. Our next signal is RTC RST hash. So we'll search over here RTC RST hash. And always note that whenever we are talking about these signals, we need these signals inside the IC. So this is the correct RTC RST hash. And this RTC RST hash is connected with RTC underscore cell, and as we have already checked, this is generated in the very first stage, so this is automatically generated. So we'll go to the third step, and the third step is V5 REF underscore sus. So we'll search for this signal V5 REF underscore sus. And you can see this is V5 REF sus is getting power from V5 REF underscore S5. So let's check V5 REF underscore S5, and you can see this V5 REF underscore sus is feeded by 3.3 volt ALW. So if this voltage is not coming over here, then we should find the location of 3.3 volt ALW from where this is generated. So let's check plus 3. We can also check the voltage at this diode, that is D14. So let's check the voltage at this diode. In another word, the voltage at this diode, that D14.
इसकी लोकेशन बताया करना सर कि D14 this is the
You can see this D14 is close to the ICH. So we will find the voltage, what voltage is coming at this D14. And you can see this is close to 3.3 volt. So in case this 3.3 volt is not coming at this diode, then we have to look for the source from where this 3.3 volt always on is coming. So we'll search. Once we do these activities for 2 or 3 kind of motherboard, then all these steps would be in your mind. So we have to do these steps for at least 3 to 4 kind of motherboard. Now let's check from where this is getting generated. Yeah, so you can see this is coming out from the 3 volt 5 volt regulator IC, and you can see this is 3.3 always on. This is coming after switching these two MOSFETs. After these two MOSFETs switch, then this PWI SRC, this 20 volt is getting converted into 3.3 volt. So we have to check if this is not generated, then you need to check these capacitors, you need to check these coils, and you have to check these two MOSFETs. And also, before checking MOSFET, you need to check the driving, whether these MOSFETs are getting this drive voltage or not. That is, drive high and drive low. So you have to check these two driving voltages, whether these two MOSFETs are getting the driving voltage or not. And this driving voltage will get enabled only when this OM2, you can see this is a dual regulator. One side it is generating plus 5 volt, another side it is generating 3 volt. This regulator this MOSFET will switch once it gets the driving voltage at gate, and when this regulator will generate the driving volt once this OM2, when it receives the OM2, and you can see this OM2 is 3V underscore EN, that is the enable signal is 3V underscore EN. So let's find from where this 3V underscore EN is coming, and you can see this 3V underscore EN is coming from 3V underscore 5V underscore EN. Let's find out from where this 3V 5V underscore EN is coming. And you can see this 3V 5V underscore EN is being generated from S5 underscore enable. So that means if there is no S5 underscore enable, there is no 3V underscore 5V EN. If there is no 3V underscore 5V EN, then there is no V5 REF underscore sus. So we have to check this S5 underscore enable. From where this S5 underscore enable is coming? S5 underscore enable. This will be coming from the IO controller, and you can see S5 underscore enable. So if S5 underscore enable is not coming, then we have to check this IO controller. As I have already discussed the IO controller class, where we have shown you the 3 important things to check at IO controller in order to turn on. The first is supply, and you can see the supply is connected with 3.3 volt RTC LDO. This has already been generated. Then we have to check for the reset, that is EC reset, and we have to check for the clock, EC reset and clock. And you can see the EC reset here at pin number 85. You can see EC reset, and EC reset is generated by this 3.3 volt RTC LDO. So we'll check in the motherboard also all these three signals. So what we have to check? We have to check for EC reset, we have to check for the supply, and we have to check for the clock also. We have to check for the clock, and we have to check whether this IO controller is communicating with the EC bias also. So four things we'll check over here. First, this voltage would already be generated because this has been generated in the previous step. We'll check this EC reset, we'll check the clock, and we'll check the interaction with the BIOS. This part we'll check whether this clock is generated or not. So now we'll check in this motherboard. We'll check in the motherboard once again. V5 will go. I'll go back. V5 REF_SUS. And this is connected with V5 REF S5. So let's check, we have already checked the pin number here that 5 volt is coming. So let's go back to check. Plus the pin 2 of this diode, whether at this pin to 3.0, let's check from where this, how this plus 5V underscore ALW is generated. Plus 5V underscore ALW. So we'll go to find this U18, the U18 3 volt 5 volt regulator IC, and we'll check all the things. That is ON1, we'll check the 5V underscore EN at this pin. Analyze this 3 volt 5 volt regulator IC, how this is working, and we'll check the voltages on this motherboard. And you can see there are two voltage limiter, one side 5 volt, another side 3 volt. So let's check the at pin number 14 whether it is getting enabled or not. So we'll check at pin number 14. Pin number 14 is 5VEN. 5VEN. 5V_EN. And you can see this 5VEN is coming from this 3V underscore 5VEN. So we have to check this one. The 5V underscore EN is being generated by this S5 underscore enable. So let's check how this S5 underscore enable is generated. And we'll go to just page number 29 and we'll find S5 underscore enable. So let's check at pin number 15 of this IO controller. My IO controller is U28. In a schematic diagram we have divided this IO controller into two parts. So we have to check the U20 pin number 15. You can see this is our IO controller. And at this IO controller we will check at the pin number 15 whether this S5 underscore enable is coming or not. And our IO is U1773. So let's check at pin number 15. And you can see at pin number 15 you can find 3.28 volt, that is 3.3 volt, that is correct volt. And if this S5 underscore enable is not coming, then we have to check for the supply. So let's check at pin number 115. whether this 3 volt is coming or not. Obviously it should come because this has already been generated in the previous step. So pin number 115. This 3.3 volt is coming over here. So supply is there, and now we'll check for the reset. Let's check on pin number 85. Pin number 85. You can see 3.3 volt. So we have start volt. So we'll check at pin number 85. Our EC once again I will show you. On pin number 85 you can see there is an arrow. So you should always count pin number like this in anti-clockwise. 1, 2, 3, 4, 5, 6, 7, 8, 9 till like this. This is anti-clockwise. So you can see at pin number 85 this is 3.28 volt. So we have met the first two conditions, that is supply and reset. Now let's check the clock, whether this IC is getting clock. So this clock is at pin number 77 and 79, and you can see this clock is being generated via this crystal. This crystal is generating these two clock, the input and output. So let's check at using oscilloscope. I will show you how to check the clocks at these two pins. So let's use the oscilloscope, and you can see this is usually you require a 100 megahertz oscilloscope for testing the latest kind of board. So let's check at pin number 77 KBC_XI. Pin number 77. You can also check over here. You can see this crystal KBCXI. You can check this KBCX1 at this crystal also. At this crystal. So let's check at the crystal. This is, you can see 1, 2, 3, 4. So we have to check at pin number 1. And you can see the sine wave. You can see the input side. Let's check at pin number 4, and you can see a high sine wave is here. That means we can let's check the parameters. Let's check the parameters, and let's check the parameters once again. You can see in the parameter the amplitude is around 76.82 when we are testing on one pin. The next side you can see the amplitude is a little less, and in the diagram you can see the one side you can see another sine wave, and the next side you can see a bigger sine wave. So this is how a crystal operates. So this crystal is also giving the correct outputs. So we have made the first three conditions, that is supply we already checked over here, reset we have checked over here, and clock we have already checked. Now we have to check the interaction of this IO with the EC BIOS chip, and you can see here is the interaction of the IO controller with the EC BIOS. Let's go to the page number 30, and we will check these 4 signals via oscilloscope. So let's go to the page number 30, and our IC is U23. So at U23 we'll check the VCC. VCC is already, it must be having this because we have already checked it. Now we will check for pin number 6. U23 pin number 6 we'll check. देखो ना हम बोलते हैं मैं सेट करा उसका ओरिजिनल बनेगा वो दिखाएंगे. Already checked that this met the first 3 conditions, that is supply, reset and clock. Let's check the interaction of this IO controller with the EC BIOS. If interaction of IO controller with this EC bias is correct, that is all four conditions are met, then this microcontroller inside, that is EC controller inside this IO controller will generate S5 underscore level. So to check this IC U23, the first thing that we will check is VCC. Since this is already been generated, we will go directly to check these two pins, that is pin number 5 and pin number 6. Pin number 6 data input. See, this is EC BIOS. We'll see the communication of this BIOS with the EC inside the IO controller using CRO. So we'll check the clock. This is getting clock from the IO controller. So we see the first pin number 6 at this BIOS chip. What kind of wave you can see in the CRO at pin number 6? This is our EC BIOS. So let's check at pin number 6. And you can see at pin number 6, and I will just modulate to see. Here clock signal would come. You can see this is clock. So it is getting a very good clock signal from the IO controller. Now we'll see at pin number 5, that is data बंद करो. Check the first three things, that is supply, reset, clock, and let's check the interaction of the IO controller with the BIOS chip. In the BIOS chip you can see there are 8 pin BIOS is used. 8 pin BIOS, you can see this is an 8 pin EC BIOS, and the important pins are pin number 8, it must be supply. This is not required because we have already checked the supply for the IO controller. So this must be there, and you can see pin number 6 and at pin number 5. Pin number 6, it is receiving clock from the IO controller. So let's check using CRO what kind of clock it is getting. So we'll check on CRO. So here you require CRO to check, and you can see it is getting clock so fast. So fast clock is coming from IO controller at the BIOS chip. Okay, and you can see like this, the clock, we are getting clock from the IO controller to the BIOS. Now let's check the data input. The data input at pin number 5. What kind of data it is getting from the IO controller? Let's see. And you can see this data input at pin number 5. At pin number 5 you can see the data input. You should always, since this thing will run at a very fast speed, so we have to always use triggering. So you can just press auto and you get the signal in the CRO. And you can see this is the data input that it is getting from the IO controller. At pin number 2, we can get the data output. So let's check at pin number 2. Pin number 2. At pin number 2, you can see this is the data output from the BIOS. Data output from the BIOS. And you can see at some time a different kind of shape is coming on. That means this BIOS is interacting properly with the IO controller. That means you can see, let's wait for some time, we will find that you can see here. If this is coming, that means interaction is taking place. So this is the way to check the interaction of IO controller with the BIOS chip. If all those four things are working properly, then the microcontroller inside the IO controller will generate the S5 underscore enable. And in my next class, I will extend this discussion. Thank you for today's class.